Hello, my name is Rachel Harvey, and today, alongside my teammates, we will be presenting the Venusian observation through low latency assessment of novel telerobotics mission, or VOLAN, by the University of Maryland Senior Capstone Team for NASA RASC-AL's 2021 competition Theme 3, Venus Flyby. Our faculty advisor is Dr. Andrew Becknell, and here you can see a breakdown of each of our team's subteams. Now for our project overview. Our mission adheres to Theme 3, the Venus Flyby, and we are to develop a mission concept to support Crew of 4 for Venus Flyby in the early 2030s, identifying various science elements to be carried on mission and deployed to the Venusian atmosphere and surface, all while utilizing low-latency teleoperation. Our mission should support longer duration human missions to Mars and deep space, and our annual budget is $2 billion per year from 2025 to 2034. Our developed mission statement is to send a crew on a Venus flyby to perform human-in-the-loop science and gather data critical to the future of human deep space flight. Here's an artistic rendering of our Volant vessel. And here is an artistic rendering of our lander trio in the Venusian atmosphere.
Hi, my name is Juan Rodriguez, and I will begin by talking about Volan's science objectives. The Volan mission is organized into three main goals. The first goal is to increase our understanding of Venus's geological history. Its surface contains features called tesserae, which are rough highlands that are some of the oldest terrain and make up 7% of the surface. They could be caused by volcanic flows or uplifting and weathering of ancient crust material. By examining this feature directly, we can gain insight on terrestrial planet evolution and how it compares to known geological models on Earth. The second goal is to evaluate the complex chemistry and dynamics of Venus's atmosphere. The middle atmosphere experiences relatively mild conditions at 1 bar, which is about 50 kilometers altitude. Since phosphine readings have already been debunked, further analysis will hopefully explain why life is not present. Direct measurements of the dynamics using modern instruments on our probes will refine our model of the atmosphere. The third goal is to study the long-term effects of the mission on the crew. They will be subjected to solar flares and radiation in general, being outside of Earth's magnetic field. The distance may also have mental health implications. Both should be another opportunity to collect data for future missions. Now I will go over the concept of operations. This image shows the mission sequence for Volant. The launches will be staggered throughout 2031 and will start with the habitation module. We will be using Falcon Heavy and Falcon 9 rockets. The last component to be launched will be the crew capsule. They will all be assembled at a 300-kilometer low Earth orbit over the course of these 3 months. By June 15th, the vessel must be assembled and begin the trans-Venus injection burn. Fuel tanks will be jettisoned after this burn, and the vessel will spend 96 days traveling. The probe stack and CubeSats will separate 40 days before arrival and change course to land or fly by, respectively. The encounter with Venus will occur September 19th, where low-latency operations will commence. Once its mission is complete, it will commence its Earth injection burn and travel back. Once within 20 minutes of Earth, the crew capsule will separate from the rest of the vehicle and use its built-in Super Draco thrusters to slow down to a reasonable re-entry velocity. This mission should be complete by June 1st, 2032. And here's a quick animation of the assembly of the crew vehicle. This image shows the entry sequence for the probe stack. Once it has slowed, the aeroshell deploys the entire load. The balloons will begin inflating to reach their desired altitudes of between 45 and 55 kilometers. The gliders will continue down with partial human intervention to decide where the best location to land is. Now I will talk about the trajectory and the Venus entry. To the right is an animation of the interplanetary trajectory. The crew vehicle will have 3 burns. The first burn of 4 kilometers per second to escape Earth, the second burn of 142 meters per second to adjust the flyby to an Earth return trajectory, and a 2.9 kilometer per second burn to reduce the velocity of the crew capsule. The CubeSats and probes will have 10 meters per second and 9 meters per second burn, respectively. The flyby will be close to Venus, and as a result, the 9 meter per second burn will be enough to point the probe stack toward the planet. This burn is small, reducing entry vehicle complexity since there's less fuel. However, this doesn't resolve the issue of the speed the probes are entering Venus. There will be high acceleration loads and a limited window, meaning that a direct entry is the only feasible option. These are some plots corresponding to the conditions of the probe stack throughout the atmosphere. As shown in the bottom left plot, for example, the highest acceleration experienced by the probe stack is 34 Gs. However, this is survivable by our purpose-built vehicle.
Hi, my name is Sam Shrestha. I'll be talking about the vessel architecture and the primary structures of the Volant mission. Given here is an image of the full Volant spacecraft assembly. Starting at the front, we have the Crew Dragon, which is used as a launch and re-entry vehicle for the crew. Next is the habitation module, from which the crew will live and operate out of for the duration of the mission. Third is the airlock, which allows crew to perform EVAs for maintenance, etc. And next is the probe stack, which houses the landers, balloons, and CubeSats. Last is the power and propulsion module, which provides power and thrust to the system. The power and propulsion module is accompanied by 4 separate but identical fuel storage modules, as well, which get jettisoned during the Earth escape delta V. And all connections in the axial direction are performed through the International Docking System standard. The primary structures to be designed are the habitation module, the probe stack, the power and propulsion module, and propellant tanks, not including the balloons and landers. Since all modules are launched on Falcon series launch vehicles, they are designed similarly. The max loads the structures will encounter are the launch vehicle loads. The first case being 0.5 Gs of lateral and 6 Gs of axial, and the second case being 2 Gs of lateral and 3.5 Gs of axial. And there is also a third case for the Earth escape delta V, though it is much smaller. On the right is an image of the payload fairing with a cylinder and truncated cone, which determine our geometric constraints, leading modules like the habitation and power propulsion modules to follow that shape, and the combination of the airlock and probe stack on one launch. In accordance to NASA Standard 5001, the safety factors used are 1.25 for yield and 1.4 for ultimate and buckling for uninhabited metallic structures, and 1.65 and 2 respectively for inhabited metallic structures. A knockdown factor of 0.65 is also used throughout for honeycomb sandwiches and isobirds. Next, 4 main studies dictated our materials and configurations for most of the primary structures we designed. They were simplified models using the maximum loading cases of the launch vehicles and staying highly conservative. The maximum load case of the Falcon Heavy being 63,800 kilograms, and for the Falcon 9 being 22,800 kilograms, both to LEO. The top 2 dictated that we should use a honeycomb sandwich design to save tens to hundreds of kilograms in mass when the structure had a margin of safety of 0. With that in mind, the bottom 2 determine the materials of the honeycomb face sheet and core. Aluminum 2024 is the face sheet, and aluminum 316's 5056.002 for the core were found to save on mass and thickness over the other aluminum options. This honeycomb sandwich design applies to the habitation module, probe stack, and the cylindrical part of the power and propulsion module, all of which use aluminum 2024 and aluminum 316's 5056 in varying thicknesses. Next, for each module, beyond the axial stress and the global buckling that was looked into in the previous trade study, trade studies were performed into other failure modes such as lateral and transverse shear stress, core compression, and local buckling modes of face dimpling, face wrinkling, and shear crimpling. This gave us an overestimate for thicknesses, which was optimized through finite element analysis and NX. Next, I will discuss the structure of the habitation module, and then we will go into the crew systems information. Here, an image of the habitation module is given on the left. It includes RCS thrusters for maneuvering and rendezvous in Earth orbit, windows for the crew, and small solar arrays and radiators for before it can get connected to the power and propulsion module. After optimizing the wall thicknesses down in FEA, the final dimensions are given in the table and the image on the right for a total wall thickness of about 17 millimeters. The structural mass of the habitation module is about 1,100 kilograms, and it has about 25 cubic meters of habitable volume for each crew member. In this slide, the load cases are given in the top left. Since it is a pressure vessel, an internal pressure of 9.5 psi was added to all of the cases. The lowest margin of safety was 0.07 in face rankling for the second case launch vehicle load. Also, a modal analysis was performed showing its lowest natural frequency to be above the threshold for the Falcon series rockets.
The Volant habitation module has 3 distinct living areas. The first area houses the crew members' sleeping quarters, control panel, avionics control unit, storage lockers for personal stowage and belongings, treadmill, and a heat compactor. The second area holds the bathroom, the galley system, food storage, an advanced resistance exercise device, or ARED, and 2 water tanks. The third area on the lowest level holds the water reclamation system, the oxygen reclamation system, 2 more water tanks, 2 nitrogen tanks, and 2 oxygen tanks. The life support systems on board Volant include CO2 scrubbers, a 2-bed molecular sieve, and SPADI-A reactor with lithium hydroxide for redundancy. Water reclamation on board the vessel will be done by vapor compression distillation due to its 96% water from urine recovery rate. To protect crew members from GCRs and solar particle events, a dual radiation protection system was designed. Bed spaces within the habitation module will be thickened with polyethylene and aluminum to serve as a radiation storm shelter in case of solar particle event. Crew members will also wear protection suits at a thickness of 5.32 centimeters of polyethylene and aluminum once again, and this dual protection method will save us a considerable amount of mass from the overall system. Now to briefly describe the airlock module. The airlock will primarily be used for maintenance of the Volant vessel as well as for any necessary extravehicular activities. It will maintain an internal pressure of 9 psi and contains a 1.65 meter hatch for ingress and egress of crew members. It's comprised of a triangular aluminum 7075 isogrid that supports a 1.7 millimeter thick aluminum 7075 shell.
Next, I'll be going over the power and propulsion module, including the structure, main propulsion system, RCS system, solar array and main battery, and thermal control systems. This is the module that generates and stores most of the power for the Volant system. It radiates heat away, and it provides thrust for the Earthscape delta V. Given here is an overview of the power propulsion module with parts labeled. Much of its propellant is stored in the 4 propellant modules not depicted here. The main load-bearing structure of the power and propulsion module consists of a honeycomb sandwich cylinder and end cap connected to a conic thrust structure. The honeycomb is made of aluminum 2024 for the face sheets and aluminum 3/16 5056.002 for the core. The thrust structure passes the thrust load from the main nozzle into the rest of the structure and is made of a conic panel supported by 8 stringers, all made of aluminum 7075. After iterating in FEA, the smallest margin of safety for the cylinder is 0.025 in face wrinkling in launch load case 2, and the minimum margin of safety is 0.2 in axial yield for the thrust structure. Overall, the module is just under 10 meters in length with a maximum diameter of 4 meters, leaving 30 centimeters radially in the 4.6 meter payload fairing for external components. The cylinder thickness is about 4.7 meters, and the thrust structure has 8 millimeter thick panels and 40 millimeter diameter stringers. The total mass of the primary structure is thus 714 kilograms. Shown here are the main engine nozzle and combustion chamber on the left, and tables for its properties and performance. It has an oxidizer to fuel ratio of 5.5 using liquid oxygen and liquid hydrogen. It uses a simple gas generator exhaust cycle, thrusting for 15.6 minutes with a maximum thrust of 506 kilonewtons and a specific impulse of 440 seconds. The whole thing is 1.76 meters in length and has a mass of just under 1,000 kilograms. In the bottom right is an image of the reaction and control system thruster package. Each thruster can provide 1 kilonewton of thrust and has a specific impulse of 310 seconds, using dinitrogen tetroxide and monomethylhydrazine. Each module has 4 of these RCS packages. They're used on each module for ease and rendezvous and will also provide redundancy for the rest of the mission. We anticipate the thrusters in total needing 13,400 kilograms of propellant for course corrections and 2,090 kilograms of propellant for assembly, which is split up among the modules. The anticipated power budget is given in the table here, with margins of 100% for contingency purposes and due to the likelihood of these power estimates being increased in further stages of development. Because Volant is in near constant view of the sun, we employ a deployable solar array and a main battery capable of powering the system for 24 hours. Due to a high efficiency of almost 32%, quad-junction gallium arsenide panels were chosen, with 10% degradation at the end of its life and using the lowest solar flux occurring at 1.21 astronomical units. The total area of the solar arrays is required to be 100 square meters. To output 26 kilowatts for 24 hours without being charged, including self-discharge, lithium-ion batteries were chosen for the main battery pack due to their high energy density and efficiency, among things. We use hexagonal packing for 52,500 cells, 150 in parallel with 350 in series to get the volume of the battery to just over 1 cubic meter and about 2,625 kilograms. The rest of the power system is shown briefly in a power block diagram in the top right. The main purposes of the thermal system are to 1. Maintain a comfortable temperature for the crew, and 2. Keep electronics and equipment within their desired temperature ranges. It is broken down into 2 subsystems, passive thermal control and active thermal control. Passive thermal control uses 21 layers of multi-layer insulation to reduce the heat from entering or leaving the spacecraft, reducing the entering heat to 500 watts. With 26 kilowatts from power usage, 500 watts from radiation input, and 500 watts produced by the crew, 27 kilowatts of heat must be dissipated by the active thermal management system. The active system uses 2 circulation loops, one internal and one external, driven by heat pumps and connected by a heat exchanger. The internal loop will absorb excess heat and transfer it to the external loop, which will use 75 square meters of deployable radiators to radiate the heat away. Key parameters of the active system are given in the table in the bottom right.
Hi, my name is Benz and I'll be covering the probe stack module. The probe stack module houses the aeroshell entry vehicle, which itself contains the 3 balloons and 3 landers. The module will have a diameter of 4.1 meters and a height of 5.8 meters. In the center is the mass summary for the module, which will total to around 3,000 kilograms, and on the right is the primary structure characteristics for the module. We'll be using face sheets and a honeycomb core as the primary structure. The face sheets will be made of aluminum 2024 with a thickness of 0.5 millimeters each, and the honeycomb core will be made of aluminum 5056 with a height of 9 millimeters. Next, we have our balloon probes. On the right here is the stowed configuration for each balloon probe, while inside the aeroshell entry vehicle. Inside each capsule, in the center is the probes, and the spherical ends are tanks which will be filled with helium and will inflate the balloons. The balloons, after full inflation, will drop the spherical tanks and reach a diameter of 4.48 meters. The probes themselves will be attached to the balloons via a 10-meter long tether cord. In the center here is the mass summary for each balloon probe, which will total to 189 kilograms. The balloon probes are designed to survive Venusian atmospheric conditions at 50 kilometers above the surface for at least 48 hours. We chose this altitude to be the designated altitude for the balloon probes because of the similar atmospheric conditions to Earth's atmospheric conditions at mean sea level. Next, we have our lander design. The landers are designed to glide down to the surface of Venus and survive there for at least 5 hours. During this time, they will conduct their experiments and send data to the crew vehicle. In the center here, we have the mass summary for each lander, which will total to 424 kilograms per lander. To predict the aerodynamic characteristics for our landers, we conducted a CFD analysis simulated under Venusian surface atmospheric conditions. This helped us generate the lift-to-drag ratio versus angle of attack data shown here on the right. Using the generated lift-to-drag ratio data, we simulated the lander's gliding dynamics and control. We used a control technique which involves controlling the bank angle and angle of attack of a planetary glider independently. On the top right here, we have the bank angle control input equation, and on the bottom left, we have the angle of attack control input. On the bottom right here, we have the simulation results for our lander. These simulation results show satisfactory performance in terms of impact velocity, forward velocity, landing accuracy, and glide duration. And that should be the end of the ProbeStack module. Thank you.
Hi, everyone. My name is Joshua Martin, and I'll be presenting Volant Avionics today. I'll quickly overview the electronics architectures of each vehicle. The overall crew vehicle will be using 3 flight computers in parallel to maintain a connection to sensors, engines, and actuators, with time-triggered Ethernet available for high data rate connections and MIL standard AS1773 available as a low data rate, rad-hardened, reliable backup for flight-critical systems. For landers, 2 flight computers will be used in parallel for actuator control, as well as for receiving commands from the human interfaces and transmitting scientific and camera data back to the crew vehicle. Lastly, the balloons are simple enough that they only require a single flight computer, which coordinates scientific instruments, communications, and an inertial measurement unit for further data collection. Communications will be mediated by line of sight between the crew vehicle and each section of the communications architecture. When close to Earth, crew vehicle segments will communicate over S-band omnidirectional antennas to the near-Earth network. For deep space communications, meanwhile, 2 1.5-meter Ka-band transmitters will communicate with the deep space network, transmitting over Ka-band and receiving over X-band. These same high-gain antennas will be used to communicate with 0.2-meter Ka-band antennas on each of the landers for high data rate transmission of live video and science data from the atmosphere and surface of Venus. Basic lander and spacecraft telemetry will be communicated over omnidirectional UHF antennas on landers and balloons, and deployable 0.5-meter UHF antennas on the crew vehicle and beacon satellites. Beacon satellites will also communicate minor telemetry updates with each other and the crew vehicle via omnidirectional VHF antennas. Here is a brief overview of the Earth to crew vehicle communications link budget. For link budgets, we sized antennas to give us an industry standard link margin of at least 3 decibels. The left 2 columns are S-band communications for spacecraft assembly and near-Earth communications, while deep space communications in the X and Ka bands are on the right. Though we expect Ka-band optimized antenna on the spacecraft to lose some efficiency in receiving X-band from Earth, as the deep space network cannot transmit, only receive over Ka-band, the link margin in the optimal X-band is sufficiently large enough that we can handle this efficiency loss as we expect. And here are the lander communications link budgets with UHF transmissions sending basic lander, crew vehicle, and beacon satellite telemetry, and Ka-band transmissions mediating lander comms on the right 2 columns. In order to mediate high gain, high data rate video and data transmission between the landers and spacecraft, both landers and spacecraft must orient high gain Ka-band antennas at each other. However, in order to localize the spacecraft, 3 8U CubeSats will serve as beacon satellites in addition to another beacon of the lander, and will broadcast position and time data to serve as reference points for lander trilateration in order to determine how the lander needs to orient its high gain antenna. At distances present towards the end of the lander operation, the omnidirectional antennas will not be useful for the 50 to 100 bits per second transmission necessary. As such, each CubeSat must be equipped with a 0.5-meter deployable UHF antenna for transmission to the landers, as well as omnidirectional VHF antennas for communication with each other and to the crew vehicle for minor telemetry updates. They will also be equipped with cold gas propulsion systems for orbital insertion and orientation, and a suite of navigational sensors. Here, as you can see, the 2-way time delay never exceeds about 0.75 seconds between the lander and the crew vehicle over the 5-hour expected operational window of the landers themselves. Thus by demonstrating the potential for robotic teleoperation and high data rate science within the Venusian atmosphere and on the Venusian surface offered by the Volant mission.
Now for cost and mass analysis. From RASC-AL's Theme 3 requirements, the annual budget of the Volant mission cannot exceed $2 billion. Cost approximations were made using equations from Arne and Wilhite, along with given launch costs from SpaceX for Falcon 9 and Falcon Heavy. Our estimated payment plan for launches begins 2 years prior to launch dates, and we're laid out with 15% of launch costs spent in 2029, 15% in 2030, and the remaining 70% in 2031. $149 million spent on launches in 2029 and about $697 million spent in 2031. These fixed launch costs were added to the calculated research and development as well as flight unit costs to create our final program cost distribution. The total mission cost is $12.358 billion in 2021 dollars. In order for Volant to support future deep space missions, launches needed to be reusable. Therefore, our launch margins had to be around 50%. Each launch has a margin at around 50% saved for Crew Dragon and its cargo launch in the Falcon 9. Masses for each launch were estimated given data from SpaceX as well as NASA analogs. In summary, humans will be able to communicate directly with our probes during their descent, landing, and operation stages with minimal latency compared to typical interplanetary comms. The Volant mission will deepen understanding of the Venusian terrain and Venusian atmospheric potential for life through usage of our landers and atmospheric balloons, as well as validate current planetary atmospheric models. The Volant mission supports the future of human deep space flight and provides an innovative foundation for future missions to Mars.